They might have explicit examples, though. They don't give that much detail, I think. Like when they say this is the basis for the rapid decay homology, sometimes they just say. Later on.
So what I will do is, I was saying on the way over, I don't know how much I have to say, maybe not 2 hours worth. I might take it a little easy. I think 5 o'clock is the normal time that we meet. So, but I'm not sure. Again, people may have other plans this week, so I don't know when there'll be more people, if there'll be more people at 5 o'clock. So I will go. Well, I'll just go at a sort of moderate pace. There's certainly things I want to say today. So, am I on? I think so. Do you? Can you hear it? Yeah. So. Last time I said a little bit about, insofar as I understand them, about exponential motives, and they appear to be things that are very important for questions in fundamental physics, as well as for their own right, in their own right, and but so that's the analog. It's a huge. It would be. It's some of it's conjectural as well, but it would be a huge generalization of the motivic Galois group, or the mixed motivic Galois group, which is already a huge step from what's understood. But the question is, exponential motives are they've a pretty well developed theory. There's just a huge amount of stuff in it. But what would be their automorphic analog? Automorphic representations are much more precise in a way. They give, in many ways, more explicit data. Motives are just often given by abstract axioms, and it's hard to know, be more precise about it. You can do their realizations, and they have a more precise form, but still it's not the same thing. And so we would like an automorphic version of the exponential mixed motivic Galois group, something which is discussed readily in this article. I mean the latter thing in the Frisson and Yosen. So we would like, so I did talk about this last time, or I just mentioned it, automorphic analog of exponential mixed motivic Galois group. So I'm going. I have planned. So I'm going to work to try to understand this better, but I not really don't understand terribly much of it. But we asked the question last time. What is this? Okay, I gave what I thought it was for a couple of moments. When I was looking at this article over the weekend, I was having my doubts about this, and I know that it seems pretty strange, actually, what I was suggesting, but so what I think it is, I'm pretty, there's a certain amount of faith here, but I'm pretty sure that it's got to come from these central extensions of adelic groups. It should come from extensions, and I'm going to say topological because they're not algebraic extensions. G tilde of A of adelic groups. GA, and the representations, I don't know what they would be called, they're not quite automorphic representations, but the representations, the irreducible representations, we could say, I won't write down pi tilde because these should be stable classes of representations or even just the unramified data attached to them. But I'll just say representations, irreducible representations of L2 of G tilde A in the decomposition of L2 G tilde of A. Now, GF is a discrete group, so that you don't get to take extensions of that unless they come from algebraic extensions of the group G itself. There's not any topological extensions, so we don't get to divide out by a bigger group in here, but this lies in here, and so we can talk about the irreducible representations in the decomposition of this in place of the irreducible representations of GA. These are automorphic representations on L2 of GA modulo GF. What am I doing? This stuff has turned my head and I'm getting the notation wrong. It's GF, of course, on the left, G tilde of A. I'm not going to change, we don't want to change the notation. It's confusing enough as it is. So GF mod GA. Now I don't know what this subject is called. It's developing. It is going to be a huge subject. I mean, for any given G, there are lots of extensions. I'm not saying perhaps for all G, but certainly for the G's that have motivic significance, or at least the ones that are associated to Shimura varieties, there are lots of topological extensions. By the way, everything I'm saying is modulo a better understanding, but I'm telling you what I think, and I hope most of what I say is correct. Every group G, a reductive algebraic group over F, for every such thing, or for most of them, there should be many of these things. So there should be many families of these exponential, many of these families of representations in place of the automorphic representations. So this should be bigger than this. So it's a huge theory, and it's very sparsely developed. Huge theory. I like to believe that Again, this is highly speculative, but I like to believe that we're talking about all of this is we're talking about conjectures, and what we want are reasonably precise conjectures. So, for example, people that do particle physics, they don't mind conjectures. Physics is conjectures and subject to verification, experimental verification. So conjectures, that's what we're doing. I mean, that's a big part of it, because it gives you, if they're correct and if they're really, really beautiful, that gives you power to work further on it. But ultimately, as mathematicians, these are going to have to be proved. Any conjecture that we talk about, if it's correct, is going to have to be proved. And I like to believe that the proof will come from beyond endoscopy. That is to say, and I know I've said this a number of times, but the decomposition, the beyond endoscopic decomposition of the stable trace formula, which we haven't talked about at all. But if that's the case, then it's going to have an analog here for this guy. It's very far from complete, and it's a very big and long, difficult project just for this. So we're thinking if it's going to be here, it's going to be ever so much more difficult. I'll just finish this sentence. And the start, you're going to have to, very little is known about this. The trace formula, the stabilization of the trace formula, endoscopy. Those are all things that are becoming in reasonable shape for this, but not for this. And so this is just an enormous road ahead of us. I mean, even if this speculation is wrong, namely the relationship between this and exponential motives, which I don't believe it is, even if it's wrong, this is a fundamental and important theory, and will occupy people for decades. Yeah, Waleed. They all should. They all should, in my opinion.
I see. By which you mean that from all of them you'll have a surjective map conjugate until we have a Galois group?
I hope so. I hope so. It's a little bit subtle, and I will talk about it now. I mean, what the small extent to which I understand it now, and also this afternoon. But just the theory of exponential motives should be wrapped up in the theory of these things, in the same degree that the theory of motives are wrapped up in these things. There are many more exponential motives than there are motives, right? I mean, exponential motives correspond to groups with potential, and there's lots of potential F, and there's lots of those for every group. So there's a whole bunch of those. They would seem to dominate just regular motives, just like the irreducible representations of these things appear that they're going to dominate the automorphic representations of these things. Yes?
This may be silly to ask if we don't have a trace formula, but how are we allowed to think of these L2 spaces for E tilde? Do they still enjoy kind of a lot of?
Oh yes, they'll have
structure.
Yes, okay. Yes. The beginning, I mentioned, I'll write it down again, but I mentioned the article of Wietek Dan and Gao. And they say at the beginning, right at the beginning, it's a very nicely written article, but right in the beginning of their introduction, they talk about the local. So these things are built out of local extensions. They're built, it's not a global, I mean, it's global insofar as you just piece together a bunch of local extensions, and the local extensions are topological extensions of the local group. But he talks about how much is actually known about the local representation of these things. A fair bit is known. Harish-Chandra Harish-Chandra worked in more general axioms than just for real groups than just real points of an algebraic group, and they include much of what's here. But we're talking global. And global, yes, I could imagine it's going to structurally be exactly. Oh,
they expected to have a theory by Einstein series.
it's done.
Oh, it's done.
It's done. I think that's fair to say. Langlands was just like Harris-Chandra. He worked. He didn't talk about Adele's, but he worked very generally, more beyond what is beyond what you would get from algebraic Adelic groups. So that's in good shape. But then the trace formula, nothing's, well, there's one notable exception. Trace formula, stabilization of the trace formula, endoscopy, that's going to be a part of the story. And then, so I'll just say that's a huge subject, largely undeveloped. Little bits of it correspond to metaplectic. Again, I won't talk about those in any detail. Groups, I don't know, did I talk about this last time? I can't remember. Metaplectic groups, they're extensions of SL2, of degree 2, They representation. I'm copying, I think I'm copying some remarks from the preface of that article G and G. So they group of representations of larger metaplectic groups, and these would be coverings of topological coverings of symplectic groups. And then something now that's approaching a system. These are they're very important historically, but they represent rather a rather sparse collection of examples of things that are over there, even though they've occupied quite a bit of attention over the last 30, 40, 50 years. But then something that's approaching more like a general theory, Berlinski, Deline, coverings. Okay, so this is can't remember if I wrote this down last time. We'll call it G. Wietek, Gan, and Van Gao. And this would be the Langlands. They call it the Langlands Weissman. Program for Berlinski. Deline extensions. All right, so what are we looking at? So our goal, let's think of it as a goal, very long term, even just as far as conjectures are concerned. So the goal is to construct a conjectural but explicit exponential motivic, exponential, mixed, Automorphic. Galois group. Okay, I'm going to write this. I've been writing GF for the automorphic Galois group as a group over attached to a number field. This would be, as always, F's a number field with a fixed embedding into the complex numbers, and this is supposed to be. We haven't actually figured out what the Q structure of this is, but it's supposed to be a group over Q. So that's what we have been talking about. So mixed, I think I've been writing a plus for mixed. The plus is then the semi-direct product of this with the unipotent group, but then I'll put a tilde on it, which should be a covering of this for exponential motives. So this would be as a pro algebraic group over Q for a number field F in C. Explicitly, so the sentence would just say explicitly, and that's the point. I guess I've said explicit there, but explicitly in terms, well, let's be greedy. Let's say, I'll mention this perhaps again a little bit later, or maybe this afternoon. Deline feels that the irreducible constituents of these should be as important for the extra information that they supply for ordinary automorphic representations as they are in their own right. So with that understanding, this should be, I think, in terms of ordinary automorphic representations. Okay, so let's no, this would be the thing that would then give the motivic group.
So this is the analog of the LF.
Oh, I'm sorry. Yes, I've. Excuse me. Motivic. Sorry. Motivic. Thank you. I'm glad somebody's awake this morning. Yes, thank you, motivic group. Okay, so let's just, is this, I think people can see this. So what we have, so I wrote a very large table that didn't seem to make too much sense, I think a week ago. But what we have, we've got the motivic Galois group, the mixed motivic Galois group, and then here's what we want, the mixed exponential motivic Galois group. And these fit in. This is a covering of Langlands Tanyama group. It's equal to the same thing here. The Tanyama group is part of the semi-simple part of this, so it doesn't change in this picture. This, however, would require an extension of Langlands Tanyama group. And this would map onto this. These all would go to the Galois group. And would be mapped into this. So I'll just write down, this is, I'll write down the reference to this precisely, perhaps a little later. This is Greg Anderson's This would be Greg Anderson's extension of TF as a reductive group, almost a CM type group, group over Q, pro-algebraic, Q, that's what this is. This is Langlands Kanyama group. And I'll just say this is the conjectural. The conjectural construction as a group over Q in terms of locally, I'll say in terms of locally, thanks to the lead, I'm taking it out where it doesn't belong, the word automorphic, but this would be in terms of something we've already talked about, of the locally compact automorphic Galois group. LF, that's what this is, and so we would be regarding this as known. This, I just, again, I said it, but this would be the conjectural extension of GF, which I'm not sure that it's quite in, Sasha will know better than me, but I'm not sure it's in quite the form that we want it. But the conjectural extension of GF described, I'll be generous and I'll say I described it explicitly. In terms of valence and conjectures. Okay, so I'm being generous and I'm going to say this is done. We've given this done. We actually still don't know what its Q structure is like. I'll be generous and I'll say that this is done. There's there to be regarded as known. And so that's this thing here. So everything in this table is known except this. And this is what we're looking for. Let me put this. This is unknown. That's what we're looking for. More precisely, what do we want more precisely? More precisely, we would like to construct. So now I really am talking about automorphic. I would like to construct an automorphic precursor to these things. So explicit, automorphic. Conjectural. Analog of the top row. This top row here. So what are we looking for there? We're looking for automorphic, locally compact. So the automorphic ones are locally compact groups. The motivic ones are pro-algebraic groups. And so what do we have? Remember, we had a locally compact group there, LF. Now this we haven't talked about at all. This is G, yeah, that's an arrow. That's just pointing to this. And I don't even know whether to expect such a group, but question, is there a mixed automorphic Galois group? That would entail, there probably is, that would entail if the motivic Galois group is basically built out of cusp forms or things, primitive representations that occur discretely in the L2 automorphic spectrum, then this would be things that come from principal series. And there's all kinds of stuff in there. But I would anticipate that we would be able to do something like that. Harder has worked hard on these things and what their analogs should give for I'm messing up the table here. What their analogs should give for motives. So I think that that's something we would want. We haven't talked about it, but then we would want the analog of that for exponential motives. That's what we're hoping for. All right. I have to watch the time. I'm teaching back in the other building at 12.
So in our description of the mixed motivic Galois groups, we use the valence as conjectures.
Yes.
Kind of putting in
some
vector spaces of dimension that are kind of predicted by the Langlands. If you do that for these principal series, is there any interpretation of like this order of vanishing that would show up there, or is it?
Let me just think for a moment. So this is something we in principle know about. So you're asking what should be its analog up there.
You can guess what a conjectural form of this mixed automorphic Galois group would be if you just kind of copy the definition.
Well, I hope that that's what it's going to be. One could hope that that's what it's going to be. I think it should. I mean, these things, when we're talking about valence and conjectures, and we're talking about orders of the points of motivic L functions, those are really automorphic L functions. That's the only thing you can really work with. The motivic L functions don't mean anything until you can prove analytic continuation in functional equation. And for that, you need automorphic L functions and functoriality and beyond endoscopy. So yes, I think so. It's just that there's a lot of them. I haven't really thought about it, but there's lots of subquotients of non-unitarily induced automorphic representations on Levy subgroups. So I'm not sure which ones one should pick and exactly how it should all fit together. But yes, the answer in principle to your question, I would say is yes. Okay, so maybe let's see. Goal. So I'll say here, what we have. So this is a long line of there are a bunch of pieces here, and I'm going to double underline them. So there's the goal. What we have. So after that, what we have. We have, and I've said this, but maybe it's because future remarks are going to depend on the little pieces that go into this, or at least speculatively, they would be related to the little pieces that go into this. What we have is LF is a fiber product over explicit data of groups LC over WF. And so I'm going to draw little arrows to this just to remind ourselves. This is the fiber product. Maybe I'll do this. Yeah, this is fiber product. Over primitive. Pairs. G and C. V not in S. That's what that is. And this thing here, let's keep all of this straight. This would be, this stands for an extension. Just reminding ourselves, KC, LC over the VE group, with KC, so this is all quite explicit. Conjecturally, KC was a simply connected simple group. Not absolutely simple, but simple as an algebraic group. And it's a simply connected form of it. So this is compact, simply connected. So that's what we have. So this is what we have, and we also have. That's this thing here. Okay, so we've got, what do we have actually? We have basically everything in these two columns. And what we want, and we also have this. So well, maybe I'll leave that out, but we have everything in these two columns, and we also have the extension of the Tanyama group, thanks to the work of Greg Anderson. Everything we've got in this box. What we want is this. That's what we have, and this is what we want. I think that's right. So in describing what we have there, I need to add GF as also a restricted direct product, but this is a pro-algebraic direct product. It's a pro-algebraic limit over the subset of data C, which are motivic of the algebraic version of this group. So TF is an algebraic group attached to the VE group. Actually, it's only attached to a piece of the VE group. That piece of the VE group, which corresponds, whose representations, as representations of the VE group, are motivic. So Langlands, he didn't talk about this too explicitly in his Corvallis article, but what he did was he took that little chunk of the Weil group. There's parts of the Weil group that don't index groups that have index representations that are not motivic. Langlands took the part that indexes motivic representations, and then he expanded it into a pro-algebraic group. That's what he did. So it's the product overall. So that's how this works. So it's a pro-algebraic group. So what is this? This is a complexification of LC. What does it mean to be motivic? So this is very important for the future, just this notion, where C is motivic if the local parameter phi v WR into LC attached. So these things are parameterized by data that parameterize automorphic representations, and it makes sense to talk about the Archimedean component of those representations. And this would be attached. I'm conjecturing that it's not going to depend on the choice of C attached to any C. These are these C's up there. So if you have an automorphic representation attached to a C, I want to know when that automorphic representation is motivic. I want to know when C is motivic. And I want it to be explicit. And how do you do that? Well, this is a map of the Weil group into a complex algebraic group. And I would ask that it be of Hodge type. Define a Hodge structure over Q. That's what that means. What does it mean to be of Hodge type? It would mean that for any finite dimensional representation of this, the composition is going to give, what would you call it, a rational Hodge structure. That's how you would select the subset that are going to be motivic explicitly from the automorphic representations that are built into this. Yes? Mm-hmm.
LC.
Mm-hmm.
LC here is a locally compact group.
That's right. That's right.
And you want this map into LC for any finite dimensional representation of LC.
Mm-hmm. Complex. Or maybe rational. Maybe rational.
This is a rational representation of a locally compact group.
Mm-hmm. Mm-hmm.
And you want that the composition with this local parameter is
defines a Hodge structure. A pure Hodge structure, because we're only dealing with this piece. A pure Hodge structure. Well, yes, if you have a finite dimensional so it's a realization of it. General maps from the Weil group into a complex vector space don't look like anything like Hodge structures. They have fractional weights, or I guess even worse. So it's a very particular condition that this be motivic. That it should be basically like so the real, I gotta go. The real, we'll talk about it this afternoon, but remind me to talk about it then. Anyway, I do find that paper on exponential Hodge. I find all of these papers really just stunning, and for the future of mathematics that they represent. And well, as is the automorphic stuff too. Beyond endoscopy, as it progresses, is going to be very exciting too. So anyway, we'll see you. We'll talk this afternoon.